Now we will start the respiratory physiology. Respiratory physiology, there is lung volumes. First of all, we'll talk about the lung volumes. Note a capacity is a sum of two physiological sums. Okay. Now, basically, you guys know the different definition of it, but I will make it very simple how to memorize these things. Okay. So just let us discuss the definition. Then I will tell you at the end how to remember this. So, inspiratory reserve volume is air that can still be breathed in after inspiration. So reserve means after inspiration, what is the reserve? That is air that can be still breathed in after normal inspiration. And tidal volume is normal inspiration or expiration. Okay, what is the volume that gets in and out during quiet respiration? Expiratory reserve volume is that volume which can be expired after normal expiration. So if the x is 500 ml, then expiratory will be 3x, that is 3 times the tidal volume. So see the e looks like 3, so that should remind you of 3x. Okay, and inspiratory is 7x, so I looks like 7, isn't it? Somehow you should think like that. Okay, it's really funny. So I looks like 7, and that is for 7x. Okay, now talking about residual volume, air in lung after maximal expiration. So suppose you expired to the full, and what the air that is left is called the residual volume. Residual volume and lung capacity that includes residual volume cannot be measured by spirometry, and this is very important, okay, concept. And talking about the inspiratory capacity, air that can be breathed in after normal exhalation. Okay, this is the inspiratory capacity. So that could be tidal volume and inspiratory reserve volume. And now I will tell you how to remember all this. Don't worry about that. Functional residual capacity is the volume of gas in lungs after normal expiration. And vital capacity is maximal volume of gas that can be expired after maximal inspiration. So this is called vital capacity. And total lung capacity is the summation of vital capacity plus residual volume. Okay, so that comes out to be whatever the vital capacity is plus the residual volume of gas present in lungs after maximal inspiration. So basically this is the all the capacity of the lungs, so total lung capacity. Now how to remember all these things? It is simple, so simple that you will laugh. Okay, just remember the word TIER, tire. Okay, tire. Okay, now go from down to above in the form of IVF. Remember, in vitro fertilization. Okay, so this is basically in vitro fertilization. I for now all these numbers entire are volume, but all the in vitro fertilization are capacity. So the IC, VC, and FC. Okay, so here you can see over here that this is the T, tidal volume, inspiratory reserve volume, expiratory reserve volume, and residual volume. These are all volume, but I, V, F, these three things are capacity. So because this is this get the value is got by the addition of two volumes or three volumes. So here how to remember? I is the first two, last two is the F. Okay, so that is functional residual capacity, and the first three, that is TIE, is the vital capacity. Also remember the vital people wear tie. Okay, so remember in that way. So vital capacity is for TIE, tie. Also here you can see I, V, and F, IVF. So if you remember tire and IVF, then you are good to go. Now X, as I said you, X is for the tidal volume, 7X is for the inspiratory because it looks like 7, I looks like 7, and E is for 3X. This is for the expiratory reserve volume. One thing that you have to remember is 2x plus 200 is the residual. By this way you can also remember the values. Now you can calculate any value that that someone asks you. And remember, total lung capacity is summation of all these tire. Okay, TIER, or vital capacity plus residual volume, where vital capacity is first 3 and the last one is the R. So don't forget this TIER and in vitro fertilization thing. Okay, now talking about taco, paco, pico, paco. Okay, so here you can see that dead space volume, okay, or physiological dead space is calculated by tidal volume into paco, pico, paco. Okay, Paco, Pico, Paco. So basically it is dead space over tidal volume. If you take this Vt down, okay, this in the denominator, here it will be equal to the dead space upon the tidal volume. This is the tidal volume, let's say PaCO2. So dead space volume will be equal to PaCO2 minus PeCO2 over PaCO, where this can be alveolar or arteriolar. It could be anything, okay. So physiological dead space is equal to anatomical dead space of conducting airway plus alveolar dead space, okay. Apex of the healthy lung is largest contributor of alveolar dead space. Volume of inspired air that does not take part in gas exchange. So basically this is the volume of inspired air that does not take part in the gas exchange. And to remember, just remember tidal volume multiplied by Paco, Pico, Paco, okay. So this is the mnemonic that I used to remember for the easy and quick calculation. Now talking about the physiological dead space, approximately equivalent to the anatomic dead space in normal lungs, may be greater than anatomical dead space in the lung disease with BQ mismatch. Now talking about the ventilation, here you can see the minute ventilation is calculated by tidal volume into respiratory rate, but alveolar ventilation is calculated by the effective gas that got exchanged. So that is by subtracting the total volume minus the dead space, isn't it? So that was the air which was ventilating the alveoli only, okay. So tidal volume can involve both, but if you remove the dead space from there, then it will become the alveolar ventilation, and that is quite logical, isn't it? So normal value, you can see over here respiratory rate is 12 to 20, and you can see if you forget by chance, just write R, okay. So that R looks like 12, and this is 2, so 12 to 20 is respiratory rate. Just remove this one line, that will remind you of 2, okay. So 12 20, you will remember that, I believe. And tidal volume is equals to 500 ml per breath, and dead space volume is 150 ml per breath. So basically while calculating, you have to subtract that 500 150 from the 500, that is tidal volume, okay. Now here I have written something about PFT after aging. So basically a patient age more than 35 experiences decrease in chest wall compliance as a result of what is it? Stiffening from the rib calcification and from increased thoracic curvature due to osteoporosis and osteoarthritis, okay. There is decrease in chest wall compliance. In contrast, lung compliance increases with age due to loss of elastic recoil. So basically lung becomes more compliant while chest becomes less compliant, particularly in the in the alveolar duct. The dilation of the alveolar duct is homogeneous as opposed to the emphysema with COPD, and is not associated with destruction of the alveolar walls, okay. Now talking about the diminished elastic recoil and collapse of the supporting tissue around the airway causes a significant rise in residual volume. However, TLC remains unchanged because the decreased chest wall compliance counterbalances increase in lung compliance, okay. So basically if they ask you what is constant in aging, then total lung capacity remains unchanged. Why? Because chest wall compliance is balancing the increase in lung compliance. So decreased chest wall compliance balances the increase in lung compliance. In addition, as residual volumes becomes much higher proportion of total lung capacity, forced vital capacity also decreases. Other age related associated changes are decrease in FeV1 and diffusion capacity, okay. Remember that. Now I will talk about the Cheney Stokes breathing, which is very important, which is basically seen in congestive heart failure, okay, but can also be seen in stroke, brain tumor, and traumatic brain injury. So what is Cheney Stokes breathing? You see the pattern. So there will be hypocapnia followed by hypercapnia. So what happens actually in this case is the patient with CHF have hyperventilation. Now just imagine if you are hyperventilating, you will wash out all the carbon dioxide, which induces apnea, okay, because carbon dioxide is the thing that causes respiration, isn't it, by activating the medulla. But here you can see if there is hypocapnia, it will result in apnea. Now if there is apnea for a long time, then there will be accumulation of carbon dioxide, which stimulates ventilatory response that overshoots the hypercapnia, causing the PaCO2 again to fall down below apneic threshold. This cycle of apnea and hyperventilation. So basically there will be hyperventilation and apnea. Hyperventilation will wash out all the carbon dioxide, leading to apnea, and apnea will cause the accumulation of carbon dioxide, which will lead to the hyper respiration again. So this cycle repeats. Okay, in Kussmaul breathings, you can see in Kussmaul breathings is basically a deep and labored breathing pattern often seen in patients with diabetic ketoacidosis. Okay, I have also written here in UWorld, patient being weaned from mechanical ventilation typically breathe at lower tidal volume with compensatory increase in respiratory rate to maintain meaner ventilation, because at low tidal volume a higher proportion of each breath is composed of dead space, and which increases the wasted ventilation, which is an inefficient breathing. So basically the one which has the patient being weaned from the mechanical typically breathe at lower tidal volume. Okay, though it is lower tidal volume, there is increase in the respiratory rate. So yeah, it is logical, because if there is low tidal volume, most of them will be dead space, so you need to increase one the other limb, that is respiratory rate. So if you increase the respiratory, that can compensate for the low tidal volume, which was wasted mostly by the dead space, isn't it? So basically you increase the rate of ventilation or respiratory rate. Now this is called pressure and volume curve. Okay, here you can see this is chest wall compliance. Okay, this blue line is chest wall compliance, whereas this red line is lung compliance. Now elastic recoil is the tendency of lung to collapse inward and chest wall to spring outward. At functional residual capacity, what happens? Inward pull of the lung is balanced by the outward pull of chest, and system pressure is at atmospheric. So basically this is just the functional curve of the lungs, you can see over here. Okay, and this is the chest wall, and our lung operate in between. Okay, balanced between these two. And if you see very carefully, this is the point. Okay, this is the point where transpulmonary static pressure is 0. At this point, these two structure, I mean to say transpulmonary static pressure, here you can see there is equidistant from these two curves, this curve and this curve. This distance is equal. Okay, and that is the point of FRC. Okay, this is the functional residual capacity. So here you can see at functional residual capacity, inward pull of the lung is balanced by the outward pull. See, in the functional residual capacity, inward pull of the lung is balanced by the outward pull of the chest wall, and system pressure is atmospheric. At functional residual capacity, airway and alveolar pressure equal to the atmospheric pressure, called 0, and intrapleural pressure is negative, prevents atelectasis. The inward pull of the lung is balanced by the outward pull of the chest wall. System pressure is atmospheric. Pulmonary vascular resistance is at minimum. So what are the things that you need to remember at this point, at functional residual capacity? So what are the things that you need to remember is, the first thing, that is inward pull of the lung is balanced by the outward pull, and the other thing, the pulmonary vascular resistance is at the minimum. Okay, at this point. So basically you can see there is more blood flow at this point. Now talking about compliance. Compliance is nothing but another term for the distensibility. So more distensible, that is to say more compliant. Change in lung volume for a change in pressure expressed as delta V over delta P, and is inversely proportional to the wall stiffness. High compliance, lung easier to fill, for example in emphysema and normal aging. Lower compliance, lung harder to fill, for example pulmonary fibrosis, pneumonia, NRDS or pulmonary edema. Surfactant increases the compliance, and hysteresis, lung inflation curve follows a different curve than the lung deflation curve due to need to overcome the surface tension force in inflation. Okay, so here you can see the inflation. See, in inflation this is the different curve than the expiration. Okay, because during inflation of the lung, you have to overcome the surface tension force. That's why this curve and this curve is different, not overlapping, and that is the concept of hysteresis. Okay, now talking about changes during aging. Aging is associated with progressive decrease in lung function, and here, as I said you earlier, that total lung capacity remains the same. So what are the increased? Anything that is 2 letter, this is the easy way to remember, is increased, and anything that is of 3 letter is decreased. For example, lung compliance is increased, residual volume is increased, mismatch, BQ mismatch, AA gradient is increased. These things are increased, and that is logical too. While decrease in chest wall compliance is decreased, that is the chest wall becomes more stiff. FVC and FEV1 is also decreased. Respiratory muscle strength can also be decreased, which leads to the impairment of cough reflex, and ventilatory response to hypoxia or hypercapnia is also decreased. Okay, so basically these things. Now talking about the hemoglobin is composed of 4 polypeptide subunit, 2 alpha and 2 beta, and exists in 2 form. One is deoxygenated form, has low affinity for oxygen, thus promoting release and unloading of oxygen. Oxygenated form has high affinity for, so oxygenated is basically relaxed form, higher affinity for oxygen, that is 300 times. Hemoglobin exhibit positive cooperativity and negative allostery. Okay, so once one oxygen is bound, the affinity for the another oxygen is increased, that is called positive cooperativity. Okay, and negative allostery is when in periphery 2,3 ppg on binding hemoglobin will cause oxygen release from the hemoglobin. So increase in chloride as H plus and CO2 2,3 ppg and temperature favors the deoxygenated form over the oxygenated form and lead to the shifting of dissociation curve to the right, increasing the oxygen unloading. And talking about the fetal hemoglobin, there is 2 alpha and 2 gamma chain, has higher affinity for oxygen than adult hemoglobin, driving diffusion of oxygen across the placenta from mother to fetus. Increases the oxygen affinity results from decreased affinity of the fetal hemoglobin for 2,3 ppg. Hemoglobin act as a buffer for hydrogen ions, remember that. And myoglobin is composed of single polypeptide chain associated with one heme moiety. Okay, so that is why there is no cooperativity, rather there is higher affinity for oxygen than hemoglobin. That's why the curve is more towards the left side. Okay, these are very important things. Thank you. We'll meet on the next section.